Hello, I'm Avish. Today we're going to discuss about matched filter and correlation receivers. Matched filter is an LTA filter used as an optimum detector to detect a pulse signal corrupted with the AWGN. It is called a matched filter because its simple response is matched to the pulsar. Block diagram of matched filter is shown in figure. Matched filter is a type of LTA filter having impulse response h of t. The input of the matched filter is the computation of incoming pulse signal g of t and additive white noise denoted by w of t having 0 mean and power spectrum density n0 by 2. So the input of the matched filter is x of t. Now output of the filter is denoted as y of t. That is sampled at t equal to capital T, and we get y function of capital T. So the first equation of the matched filter is input of the LTI filter denoted as x of t, which is equal to the y of t plus w of t. Here w of t is the additive white noise, g of t is the pulse signal. So the input of the LTI filter is noisy pulse signal. After linear filtering, we get y of t, that is equal to g naught t plus n of t. Here g naught t is the linear output of corresponding pulse signal g of t, and n of t is the filtered noise. And the purpose of the matched filter is to maximize the output signal to noise ratio. So we next discuss maximization of output signal to noise ratio. For this, we again consider a block diagram of matched filter having input signal. Here y of t is equal to g naught t plus n of t. Here our requirement is to maximize the signal to noise ratio. So the signal g naught t is so far greater than filtered noise n of t. To make this requirement, instantaneous power of the signal g naught t at t equal to capital T is far greater than the average power of the filtered noise, and this equivalent to the maximizing peak pulse signal to noise ratio, and it is denoted as eta and is equal to modulus of g naught t square by expectation of n square of t, where modulus of g naught t square is the instantaneous power in output signal. E is the statistical expectation operator. Expectation of n square of t is the average output noise power. In order to maximizing peak pulse signal to noise ratio, we solve eta, that is eta equal to modulus of g naught t square by expectation of n square of t. So we first derive numerator g naught t square. For this, we consider incoming signal g of t. After filtering using LTA filter, we get g naught t. We know that output of the LTA system g naught t is equal to the convolution of g of t and h of t in the time domain. Here we use a property of the property of the Fourier transform, that is convolution in time domain is equal to the multiplication in frequency domain. So we get capital G naught f is equal to capital G of f into capital H of f in frequency domain. Now we use this equation G naught f is equal to G of f into H of f. That is the frequency domain representation of G naught t, and in order to get this time domain version, we take an inverse Fourier transform. So we get G naught t is equal to integral minus infinity to infinity capital G of f h of f e raised to j 2 pi ft df. After converting into time domain, we can sample at t equal to capital T. After sampling, we get modulus of g naught t square is equal to modulus of integral minus infinity to infinity capital G of f h of f e raised to j 2 pi ft df square. Next, we have to find the denominator. That is e expectation of n square of t. For this, we consider the noise signal, the input of the LTA filter, that is the matched filter, that is w of t. W of t is the white noise. It has a power spectrum density of n0 by 2. After filtering, it is converted into n of t, that is called the filtered noise, and power spectrum density of the filtered noise is denoted by s suffix n function of f. Power spectrum density of filtered noise is simply equal to power spectrum density of input noise into square of the magnitude of transfer function h of f. With the help of power spectrum density of filtered noise, we can determine the average power of output noise, that is n of t. For this, we use expectation operator of n square of t is equal to integration of Sn of f df. In place of Sn of f, we can rewrite n0 by 2 h of f square. At this point, we got the numerator and denominator. So, we can find the pulse signal to noise ratio. It is denoted by eta. And it is the ratio of g naught t square by n of expectation of n square of t. So, we simply put the values. We get the peak pulse signal to noise ratio, eta. And in order to get the maximized signal to noise ratio, we have to find the solution. Here, numerator terms can be solved using Schwarz inequality. According to this, phi 1 of x and phi 2x are two complex real variable, two complex functions in real variable x. And these complex functions satisfy the following conditions. That is, integral minus infinity to infinity modulus of phi 1 of x square dx is less than infinity. Also, integral minus infinity to infinity phi 2 of x square ds is also less than infinity. This means that complex functions should have a finite value. So, in Schwarz inequality, phi 1 of x and phi 2 of x are complex functions and satisfying the conditions. So, we can write modulus of integral minus infinity to infinity phi 1 of x phi 2 of x dx is less than or equal to integral minus infinity to infinity phi 1 of x square minus integral minus infinity to infinity phi 2 of x square dx. This can be right if and only if phi 1 of x equal to k times phi 2 star x, where phi 2 star is the complex conjugate of phi 2x. So, in order to solve the noise ratio, signal to noise ratio, we use Schwarz inequality at the numerator side. So, we assume x1 of phi 1 of x equal to h of f and phi 2 of x equal to g of f e raised to j 2 pi ft. So, the numerator, that is integration of g of f h of f e raised to j 2 pi f t df mod square less than or equal to the integration g of f square integration h of f square df. Here g of f e raised to j 2 pi ft can be written as modulus of g of f. So, we can eta can be written as eta less than or equal to integral minus infinity to infinity in the modulus of g of f square integral minus infinity to infinity h of f square divided by n0 by 2 integral minus infinity to infinity h of f square df. Here h of f terms get cancelled, so we can write eta less than or equal to minus infinity to infinity modulus of g of f square divided by n0 by 2. Rearranging, we get eta less than or equal to 2 by n0 integral minus infinity to infinity g of f square modulus of g of f square df. And this is the relation from which we can determine the maximum signal to noise ratio in order to optimum detection using matched filter. From this relation, we see that theta does not depend on h of f, that is called the transfer function of the filter, and depend only upon signal energy and noise power spectrum density, that is n0 by 2. From here, we can find the maximum peak pulse signal to noise ratio, that is eta max. So, eta max can be written as eta max is equal to 2 by n0 integral minus infinity to infinity modulus of g of f square df. This can be written if and only if h of f is equal to k times g star of f e raised to minus j 2 pi ft. This is according to phi 1 of x equal to k times phi 2 star of x. Phi 2 star is the complex conjugate of phi 2x. Here phi of x equal to g of f e raised to j 2 pi ft, and its complex conjugate is g of f star e raised to minus j 2 pi ft. Now this is in frequency domain, so our next step is to find the inverse Fourier transform of h of f in order to get the impulse response h of t, that is called the optimum impulse response of matched filter. The inverse Fourier transform of h of f is given by integration h of f e raised to j 2 pi ft into df. In place of h of f, we can write k into j star of f e raised to minus j 2 pi f capital T. So h of t is equal to k into integral minus infinity to infinity j star of f e raised to minus j 2 pi ft e raised to j 2 pi ft df. So which is again equal to k into minus infinity to infinity j star of f e raised to minus j 2 pi f into capital T minus small t df. For a real signal, g star of f is equal to g of minus f. So we can write h of t is equal to k into integral minus infinity to infinity g of minus f e raised to minus j 2 pi f into t minus t df. And the inverse Fourier transform of right hand side is k into g function of t minus t, that is called the optimum impulse response of matched filter in the time domain. So we can see that to get the optimum detection using matched filter, the signal to noise ratio should be maximum for the impulse response of the filter, which is exactly a reversed and a time delay copy of the transmitted signal g of t. Now let's look at some properties of matched filter. The first property says that the spectrum of the output signal of a matched filter with the matched signal as the input expect for a time delay factor proportional to the energy spectral density of an input signal. So we get the equation phi naught f is equal to modulus of phi naught f square e raised to minus j 2 pi ft. This is taken as the equation number 1. Let's look at the second property. The output signal of a matched filter is proportional to the shifted version of the autocorrelation function of the input signal to which the filter is matched. So now we take the IFT, inverse Fourier transform of equation number 1. So we get phi naught t is equal to r phi of t minus t. R phi of tau is the autocorrelation function of the input phi of t. Now look at the third property. The output signal to noise ratio of a matched filter depends only on the ratio of the signal energy to the power spectral density of the white noise at the filter input. So look at the equation. E of expectation of n square of t is equal to n0 by 2 integral minus infinity to infinity modulus of phi of f square df, which is equal to n0 by 2 e. Using Rayleigh energy theorem, the output signal to noise ratio has the maximum value. So SNR is equal to E square by N0 E by 2. Rearranging and cancelling the terms, we get 2E by N0. Now, the fourth property says that matched filtering operations may be separated into two matching conditions. Spectral phase matching that produces the desired output peak at the time t, and the spectral amplitude matching that gives the peak value its optimum signal to the noise density ratio. In polar form, phi of f can be written as modulus of phi of f e raised to j theta f. Phi of f is the amplitude spectrum and theta f is the phase spectrum. Filter is said to be spectral phase matched to the signal phi of t is the transfer function. So h of f can be written as h of f is equal to modulus of h of f e raised to minus j theta of minus j 2 pi ft. The output of the filter phi naught of t is equal to integral minus infinity to infinity h of f phi of f e raised to j 2 pi ft df, which is equal to integral minus infinity to infinity h of f modulus phi of f e raised to j 2 pi f t minus capital T df. Here the modulus h of f and the modulus phi of s is real and non-negative. So phi naught dash of t is less than or equal to phi naught dash of capital T, which is equal to integral minus infinity to infinity modulus phi of f h of f df. So here therefore modulus h of f is equal to modulus phi of f. It is standard matched filter. Next topic is correlation receiver. It's a radio astronomy receiver in which either the noise power from a signal antenna is split and multiplied with itself, or the noise power from the two arms of an interferometer are multiplied together. Signals that are uncorrelated, that is completely unrelated, give an output whose average value is 0 when multiplied together. Correlated signals, however, produce components near zero frequency that gives a steady deflections in the output of the multiplier. In addition to their use in radio interferometry, correlation receivers are also used to reduce the effect of interference and of changes in the gain and other parameters of the system. We note that for an AWGN channel and for the case when transmitted signals S1 of t, S2 of t, etc. Sm of t are equally likely, the optimum receiver consists of two subsystems, which is detailed in the figure. The first figure is detector and the second figure is a vector receiver. The first detector part of the receiver is the first figure. It consists of bank of m product integers or correlators supplied with a corresponding set of coherent reference signals or orthogonal basis functions phi1 of t, phi2 of t, etc. phi n of t that are generated locally. This bank of correlators operates on the received signal x of t in the interval 0 less than or equal to small t less than or equal to capital T to produce the observation vector x. Moving to the second figure, the second part of the receiver, namely vector receiver, it is implemented in the form of a maximum likelihood detector that operate on the observation vector x to produce an estimate m cap of the transmitted symbol mi, where I equal to 1, 2, etc. m in a way that could minimize the average probability of the symbol error. Now look at this equation. Sigma j equal to 1 to n xj skj minus 1 by 2 ek is the maximum for k equal to I. Ek is the energy of the transmitted signal sk of t. Ek is equal to sigma j equal to 1 to n s square kj. In accordance with this equation, the n elements of the observation vector x are first multiplied by the corresponding n elements of the m signal vectors s1, s2, etc. sm, and the resulting products are successively summed in the accumulator to form the corresponding set of inner product s, sm, where x, sk, where k equal to 1, 2, etc. m. Next, the inner products are corrected for the fact that the transmitted signal energies may be unequal. Finally, the largest in the resulting set of numbers are selected and a corresponding decisions on the transmitted message is made. This is the working of correlation receiver. Thank you.